Share screen start. All right, let's share screen. Usual routine. All right. So I've got quite a bit to review here from last time. A lot of details there, but this is basically concerns the Lippmann-Schwinger equation, which engages Green's functions. You can't understand it without that, and Green's functions and operators. So I've got a page and a half here, something of summary of more or less what we did last time. So the Green's operator is a function of a complexified energy I called Z here. It can be any value in the complex plane. This is defined as 1 over Z minus the Hamiltonian. It isn't defined everywhere in the complex plane. In particular, it's not defined on the real axis when you're on a discrete eigenvalue of the Hamiltonian bound state. And on the positive real axis where you have a continuum, the Green's operator has a branch cut. It says a discontinuity across there. But in any case, this is defined for all values of complex energy with a non-zero imaginary part, and it's just simply 1 over Z minus H. We define the Green's operator with two possible signs, plus and minus, on the real axis by taking the limit as the complex energy approaches the real axis, either from above or below, giving us the incoming and outgoing energy-dependent Green's operators. The Green's functions are the matrix elements of the operators in the X representation, which you can write out as a matrix element or as a function like this, XX prime and E. We worked out, so this applies for any Hamiltonian H here, this G here, G plus or minus here applies to any Hamiltonian H. But if it's the free particle Hamiltonian, we'll put a 0 subscript on it. That 0 means free particle. Put that in here. It's free particle. And without the 0 subscript, it means the full Hamiltonian. Usually in a scattering problem, it'll be the full Hamiltonian. And we worked out what that is. Actually, I didn't work it out. I just kind of outlined the derivation of it. There's some algebra to do it. But you work it out and you find the explicit formula for the Green's function for the free particle, both the incoming and outgoing, the plus and minus signs here. And it's e to the ik, plus and minus ik r over r, where r is the distance between x and x prime, the source point and the field point. These represent incoming and outgoing spherical waves. This is for positive energy. And for negative energy, it's a damped exponential like this, e to the minus kappa r over r. All right, anyway, so that's the story about Green's functions and operators. In scattering theory, we want to solve the Schrodinger equation, which I've rearranged here in a slightly different form than the usual one, with the E minus H0 on the left-hand side. We interpret the right-hand side as a source term, and then integrating that over the Green's function for the free particle Hamiltonian. Free particle, because that's the operator that appears on the left-hand side, is the free particle operator. So that's why you put G0 here. Integrate that over the source term, which is V times psi, and add a solution of the homogeneous equation, and we get a solution of the full Schrodinger equation. This is a scattering solution. This phi sub k, by the way, is tonight and also in the previous lecture. This is a free particle. The wave function is e to the I k dot x, and it's normalized by dividing by 2 pi cubed, which gives you a convenient delta, 2 pi 3 halves, excuse me, which gives you a convenient delta function normalization. Anyway, the result of this is that the scattering solution, psi itself, it's the real scattering solution you want for the scattering problem, depends on the wave vector of the incident wave, which is this phi k, which is this e to the ikx here. So I put a k subscript on psi, both here and over there. And the result is that we get the Lippmann-Schwinger equation, which is, let me circle it here in red here. That's the Lippmann-Schwinger equation. You can make it even more explicit by putting in the explicit form for the Green's function, the free particle Green's function, in the kernel of this integral transform here. The two terms here, the incident wave is the first term and the scattered wave is the second term. Scattered wave is represented as an integral over the potential with little radiated waves coming out from them, like they were little antennas situated at each point of the scatterer. You can write this in Ket language also, which is more efficient. And the Ket language version of it, I don't know where these red spots came from, unless my pen, oh, my pen is leaking. That's where it came from. Sorry. Here, excuse me. I need to excuse me a second. Get a wet cloth here. I thought I had a wet cloth here. Maybe I don't. Yeah, here, let me get this here. Red. I got red ink on my fingers. Excuse me a second here. Yeah, it's really a mess. Okay, I won't use that red pen tonight. I'll throw it away even. Anyway, what I tried to circle here is in red is the Lippmann-Schwinger equation written in Ket language. Here's the exact solution psi sub k. Here's the plane wave free particle solution just indicated simply by k, rather phi sub k and k here mean the same thing. They're the free particle solutions, wave vector k. And here's the Green's operator, here's the potential, and here's the exact wave function. And either of these two things are the Lippmann-Schwinger equation. Now then, if we take the Lippmann-Schwinger equation, we can rearrange it by bringing the psi k term over to one side, bring it over to the right side, and put the k on the left side. So we get the free particle solution is equal to this operator, this particular operator, multiplying onto the exact solution. This shows that if we can invert this operator, we can then solve for the exact solution in terms of the incident plane wave. So let's define the inverse of that as omega plus of E, it's parameterized by E because the G0 depends on E, is this operator 1 minus G0 V to the inverse. This is called the Muller wave operator, omega plus of E. Now actually, in dealing with Green's functions, it's oftentimes, there's two of them, there's a plus and a minus, which are the limit from values of energy in the complex plane. It's oftentimes more convenient, it's easier to write too, to go back to the case where the energy variable is complex and then worry later about taking limits, because at least that gives you a common notation for both the plus and minus versions of it. And if we do this, this leads us to define a version of the Muller operator that depends on a complexified energy, which is 1 minus G0 of the complex energy Z times V inverse. And then you can define omega plus or minus as the limit as epsilon goes to 0 of E plus or minus I epsilon. So that's the meaning of the omega plus here. It's the limit of this omega of Z coming in from the upper half of the complex plane. Anyway, this omega plus of E is what we need to invert the operator in the Lippmann-Schwinger equation and solve for psi sub k. So we do that, and oops, I need a piece of paper here. We do that, and this gives us the exact solution is the Muller wave operator times the incident wave, which, to remind you, here is the Muller wave operator omega plus of E. Now what we do is we obtain the Born series. The Born series is a formal power series expansion in powers of the perturbing Hamiltonian, which here is the potential. And it's obtained just by formally computing the inverse of 1 minus x, and it just gives you 1 plus x squared and so on. Or in operator language, it's powers of this operator G0 plus of E multiplied times potential, just first power, second power, and so on going on out. Gives us an infinite series. And so this is an expansion of omega plus of E and powers of the potential. If we now take this and plug this into this rearranged version of the Lippmann-Schwinger equation, we obtain an explicit solution for the scattered wave in terms of powers of the potential. And here it is. The first term is the incident wave. What you'd have in the potential were 0. Here's the first correction terms, linear in the potential. Next one's quadratic, and so on. And this is the Born series. So this is the Born series for the scattered wave function, the scattering problem. Okay. Now, something else we did last time was we used the Lippmann-Schwinger equation, taking the asymptotic limit of it, in which the observation point receded to a large distance, looking at the asymptotic form of the scattered wave. That's represented as an integral, but we can take the asymptotic form of that when the field point is at a great distance, which we did last time. And if you do that, you obtain an expression for the scattering amplitude. That's to say, the scattered wave turns into e to the IKR over r times a function we can call f, depending only on angles. That's the scattering amplitude. And also, moreover, we get an explicit expression for f, which is given here. It's some constants minus 4 pi squared m over h bar squared, multiplied times the matrix element of the potential taken on one side. Well, I need to explain what K prime here is. Back when we were doing central force scattering, the scattering amplitude F was indicated as a function of theta and phi. It's a function of angles because it tells you the angular dependence of the scattered wave. But here I'm writing it in terms of K, these two vectors, K and K prime. The K vector is the wave vector of the incident wave, and the K prime is the direction of the observer, indicated by another K vector of the same magnitude. It's in effect as the local wave vector that one would see at a large distance, like where the detector is. It's a wave vector of the same magnitude because of conservation of energy, but it's traveling outwards in the direction away from the scatterer. So this is just a notation for the scattering amplitude that allows us. We don't have to have the incident wave going in the z direction. You see, you can have it in any direction. That's the advantage of this notation. So this is a function of these two k vectors, although the k vectors are not independent because they both are required to have the same magnitude. But the direction of k prime can be anything. It's a scattered direction. So this is the incident direction and the scattered direction. In any case, it turns out we get a formula for it, and it's expressed in terms of these constants multiplied times the matrix element of the potential energy, on the one hand with a plane wave moving out in the direction the scattered direction on one side, and on the other side we've got the exact solution parameterized by the incident wave k, psi sub k, like that. Not a solution, explicit solution for the scattering amplitude, because if we don't know what psi sub k is, we can't evaluate this. But nevertheless, a very interesting relationship between the exact wave function psi sub k and the scattering amplitude, and a non-trivial one as well, because this integral only involves the value of psi sub k where the potential is active, that's to say short distances, whereas the f is an asymptotic property, and then they're connected together by this formula. It's really a remarkable result, actually. In any case, if we then take the Born series for psi sub k and plug it in, like right here, like so, then what we get is the Born series for the scattering amplitude. So this is the f here, and becomes equal to the same prefactors, the same constants out front. And we get a series of matrix elements like that. The first term is the v sandwiched between k and k prime. Now the k here is the incident k, and the k prime is a scattered k. You see, that's what this represents now. But there's correction terms where we have v, g0, v. The next one would have v, g0, v, g0, v. It would have 3 v's and 2 g0s. That would be the term that's cubic in the potential, and so on. So here you see the expansion of the scattering amplitude and powers of the potential. I mentioned earlier, back when we were doing time-dependent perturbation theory, that the Born approximation was a high-energy approximation. It's valid when the energy is high. This is another way of saying that it's valid when the potential can be treated as a perturbation. If the kinetic energy in effect is large, if H0, the kinetic energy, is large compared to the potential energy, then it's reasonable to expect a power series expansion in the potential to be valid. So that's what we're getting here with the Born series. Part of the reason we're deriving the Born series here is because it's easy to do in this formalism, but we get the higher order terms, which we didn't see in time-dependent perturbation theory. Let me remind you, to go back a little bit, that when we did central force scattering, there was no condition on the energy. We had both high energy and low energy. In fact, we studied low energy scattering. S-wave scattering is low energy scattering. So we were able to access the low energy regime by means of the partial wave expansions, which applies in central force scattering. In any case, now we're using Green's functions, and using that, the high energy limit, the Born series, is the easiest thing to derive, which we've done here. So this is the Born series for the scattering amplitude, giving you all the corrections. These series don't necessarily converge. In fact, typically they don't converge, but they may be asymptotic, which is to say that you may be able to get a high degree of accuracy out of them before the series begin to diverge. Something like Stirling's approximation for the gamma function. All right. Anyway, that's kind of a summary with a little more detail of what we did last time. Are there any questions about that before we go on to with this tonight? Okay.
Is it somehow possible to compare G naught V to the identity and say whether it's smaller or greater?
You mean you compare the G naught to the identity?
Yeah,
Well,
in the boxed equation, I guess in the expansion to say whether the
yeah.
series might converge or not.
Oh, yes, you can. I mean, there's a question about how big is the correction. There's a question about the region of the range of validity of the Born approximation.
Right.
And this is discussed in the notes. You can concoct a crude criterion for the validity of the Born approximation, and that's actually there's a section in the notes on that. I won't lecture on it, but take a look at it if you want. It's kind of straightforward to see. By the way, one of the things you'll find if you study that is you'll see that the conditions on the conditions of validity in the Born approximation are actually not met by the Coulomb potential. They're not met for any value of the momentum. I mean, here's the deal: is that as I keep saying, it's a high energy approximation. It works best at high energy. So for some typical potential, randomly chosen potential, if you make the energy high enough, the Born approximation is going to work. But for the Coulomb potential, that's not true. There's no limit on the energy. No matter how high it goes, it still doesn't work. The Coulomb potential fails across the board. That actually comes out from this as quantitative criterion on the validity of the Born approximation. All right.
I was curious, is the Dyson series valid for that case that you were just talking about?
Well, the Dyson series is also an expansion in powers of V, so it's very closely related to the Born approximation.
Okay.
In fact, to a certain extent, these Green's these series here, these Dyson, excuse me, this Born series here for the wave operator or for the Green's operator, I'll show you that in a minute. In a sense, there's a certain sense in which they are Fourier transforms of the Dyson expansion. It's a little more subtle than that, but that's basically the idea. You're going from the time domain into the energy domain.
Oh, okay.
These Fourier transforms are not entirely straightforward because remember, we needed to introduce these damping factors to make them converge to get these Green's operators. And then we found there were two Green's operators for forward time and backward time.
Mm.
So that complicates the picture. But the basic idea is it's Fourier transforms. Or one-sided Fourier transform, by the way, is also called a Laplace transform. They're very similar objects.
Okay.
All right. All right. So in time-dependent perturbation theory, we worked out the first Born approximation by those special techniques that we used. And now we've got another expression for it. Let's compare the two. First thing tonight, let's compare the two and see if they agree. So the first Born approximation would be just to take this first term here. Well, this first term here just involves the matrix elements of V. If I write this out as an integral, it becomes the integral d cubed x prime. And then we have, it's going to be, it'll turn into this, it'll turn into e to the minus I, k prime minus k, dotted into x, times the potential V of x. By the way, the potential V of x doesn't have to be a central force potential here. I think that's clear from the formalism. And then by the way that we normalize these wave functions, you get a 2 pi cubed in the denominator here. Anyway, that's what this integral turns into. That's what this matrix element turns into. However, by our conventions that we've been using in this course for the normalization of the Fourier transform, this becomes the same thing as 1 over 2 pi to the 3 halves times what we call V tilde of k prime minus k. If I plug that in here, then I get an explicit formula for the scattering amplitude f of k and k prime, and first Born approximation is equal to minus the square root of 2 pi times the mass m divided by h bar squared times the Fourier transform of the potential evaluated at k prime minus k. And so this is first Born. And then squaring this to get the differential cross section, d sigma d omega, we get 2 pi m squared over h bar to the fourth times v tilde of k minus k prime squared, which is in fact the same formula we derived earlier by time-dependent perturbation theory. We got it again, except now we have the possibility, if we're motivated, to calculate higher order corrections. You may notice, by the way, that the cross-section d sigma d omega is the square of the absolute value of f. So if we included the higher order corrections, you're going to get as a leading term what we just derived here, this square here, but you'll also get interference terms between the various components of the F series. So these various order terms will interfere with one another in producing the total cross section. It's interesting that to do things like confirming the optical theorem, one needs to use the whole series. You can't just take it one term at a time. The series is coupled together in a funny way when you check the optical theorem. All right, so that's the confirmation, if you like, of what we did with the first Bohr approximation. Now, the next topic I'd like to take up has to do with, is exploring the more properties of the Green's operators and how they relate to the Lippmann-Schwinger equation and scattering solutions. There's a whole world of very interesting formalism out there regarding the scattering solutions, and I'd like to give you an introduction to it. So to begin with, let me call your attention to the exact Green's operator G of Z, which is 1 over Z minus H, and contrast this with the unperturbed Green's operator G0 of Z, which is 1 over Z minus H0. When we let Z go to the real axis, it's this G0, which was used in the Lippmann-Schwinger equation, and we got an explicit formula for it. But the exact Green's operator for the full Hamiltonian, that's this H here concludes the potential, is quite an interesting object. I pointed out in my earlier lectures on Green's operators that the Green's operator contains within it, in a sense, all of the, by the Green's operator, I mean, this is sometimes called the resolvent, by the way, when it's considered as a function of a complexified energy. So resolvent and Green's operator mean the same thing here. If one knows the resolvent operator for all values of the complexified energy Z, you have effectively solved everything you might want to know about the quantum system, because the poles, the singularities of this operator exist on the negative energy axis, and those are the discrete energy eigenvalues of the bound states. The residues of those poles are the projection operators that give you the energy eigenfunctions. Likewise, I'll show you in a little while, knowledge of the Green's operator resolvent G of Z allows us to explicitly compute the scattering solutions. I'll show you that in a minute. So in effect, solve the Lippmann-Schwinger equation, or effectively find that Muller operator. And in fact, they even also allow you to go even beyond that. You can find the resonances as possible as well. All right, so there's a lot of interest in G of Z. And what I'd like to begin with tonight is to derive some identities which are satisfied by G of Z. So let me start by writing down a trivial identity. We'll work with a complexified Z. We can later on let it approach the real axis to get the Green's operators we need for Lippmann-Schwinger equations. Let's consider Z minus H0. I'm going to write down a trivial identity. I'm just going to take Z minus H0, and I'm going to subtract the potential, and then I'm going to add the potential V. Subtract it and add it and subtract it like that. Well, this gives us Z minus H for the first term plus V. You see, this whole thing is just Z minus H. All right, now let's take this equation and let's multiply. So let's write this another way. Let's write this as G0 of Z inverse is equal to Z minus H is G of Z inverse without the zero subscript, you see, plus potential V. Now let's take this equation and multiply by G0 of Z from the left-hand side. And if we do, we get the identity 1 is equal to G0 of Z times G of Z inverse plus potential V. Plus G0 of Z times potential V. And now let's take this equation, let's multiply by G of Z from the right-hand side. And what we get is, we get an equation. I'm going to write it down on another page here. I think it might be a good idea to save it. What we get is, you're going to get G of Z on the left-hand side here is equal to, it's going to cancel the G of Z inverse there. We get G0 of Z for the first term. And for the second term, we get G0 V times G. G0 of Z times V times G of Z. So this is an interesting and useful identity for the Green's operator. Let's see, I've got a speck of something on my screen or something here. All right, there we go. No, excuse me, it's this screen here. Okay, there it goes. All right. Now, if we multiplied by G0 on the right-hand side first, and then G of Z on the left-hand side second, we get a slightly different identity. It says that G of Z is equal to G0 of Z plus G of Z times V times G0 of Z. Two formulas look almost exactly the same, and in fact, they only differ from one another by the ordering of the factors in the second term. It's kind of a surprise that these two things are equal to one another, but they are, as it turns out. Anyway, these are interesting identities involving the exact Green's operator and connecting them with the unperturbed Green's operator. Now, what are they good for? Let's look at the first equation. It turns out the first equation is actually, it gives us something that's like a Lippmann-Schwinger equation, but one in which the unknown is, rather than being the wave function or the scattered wave, is rather the exact Green's operator of the full system. To see this, allow me to take this Z complex Z. Let's make it E plus I epsilon. Let's let the epsilon go to 0. So these turn into our G plus Green's operators. They're both the unperturbed one and the exact one. And then allow me to sandwich this by X and X prime on the two sides in order to create Green's functions. So if I do this on the left-hand side, what I'm going to get is I'm going to get the exact Green's function for the exact system G. It's going to be G of X prime and energy E. That's come from the first term here. That equals on the right-hand side is going to be G0 of X prime and energy E. And then we've got the product of three operators that I'm sandwiching between X and X prime on the two sides. So I need to do an integral transform in order to do the product of matrix elements in the middle. So we get plus an integral. Let's make it over d cubed x prime. Excuse me, x double prime. G0 plus. These are all pluses here. G0 plus of x double prime and energy E, potential V of x double prime. And then the last one is G of x double prime, x prime, and energy E. All right, that's what we get. I should have stretched it out further on the page so it's not so crammed together. Let me pull it over like that. Now I claim that this is actually a Lippmann-Schwinger equation for the exact Green's operator. And to see why that's so, let's compare it to the Lippmann-Schwinger equation for the wave function. It would be psi k of x is equal to, I'll call it phi k of x. That's the plane wave, the incident wave here. I'll write this integral. I'll make it x double prime to make it look like the integral up above. We have G0 plus of x double prime and energy E times potential V of x double prime times psi sub k of x double prime. And what you can see is that the G0 appears here in the same place with the same arguments. The potential appears in the same way. The corresponding to the free particle solution here is the free particle Green's operator, or Green's function, excuse me, in the first equation. And corresponding to the unknown psi is the unknown Green's function for the full system, both here and there. So these two equations have exactly the same structure, and techniques that are used for solving the Lippmann-Schwinger equation can also be used for solving the exact Green's function. In particular, there's a Born series for the exact Green's function. It's a straightforward application of what we did a minute ago with that Muller operator. In fact, let's do it. Let's take this. Let me show you the Born series for the Green's operator. So here's that. Let's take the first line here. Allow me again to make Z equal to E plus I epsilon. Let the epsilon go to 0. If we do, what we get is G plus of E. I'm really just rewriting a special case of the first equation. G plus of E is G0 plus of E plus G0 plus of E times potential V times G plus of E. But that can be written in the following way as, let's see here. Let me do it. Let's see. Am I doing this right? Yes. actually, let's see here. Excuse me, I'm not quite doing this right. I know what I want to do. I want to, let's see, I'm getting myself confused here. What I want to do is to, I want to solve this for the G0 plus of E. G0 plus of E, then this, yeah, because we have two factors of G plus here. I solve for the G0 plus of E, bring this, this is equal to 1 minus B times G0 plus of E. Excuse me. Let's do it right. Sorry, let's do it right. Solve for the G0 plus of E. We get G0 plus of E is equal to yes, 1 minus G0 plus of E times potential V multiplied on the G plus of E. Okay. I brought this term over to the other side. There's a common factor of G plus on the right, which is factored out like this. And the first coefficient is 1. The second one is with a minus G plus V times V. We get this. So this is exactly similar to what we have with the Lippmann-Schwinger equation, where we had psi k is equal to the same factor, 1 minus G0 plus of E times V times phi k, which we just called K, like this. And this operator is what we call the inverse omega of E, omega plus of E inverse. This is, by definition, is the inverse of the Muller operator. So inverting that, bringing it over the other side, we multiply this out and obtain the Born series. If we do the same thing with the Green's function equation, what we have is we have the exact Green's operator, G plus of E then, is equal to omega plus of E multiplied times G0 plus of E. So in other words, the Muller operator not only maps the incident plane wave into the exact scattering solution by multiplying onto the plane wave or the wave function. If we multiply into the left of the unperturbed Green's operator, what we get is the exact Green's operator. So this is a way of telling you that if you know the Muller wave operator, you once again you solve the whole system, because now you can find the exact Green's operator and solve the whole thing. You can find the wave function, the exact scattering solutions. All right. Anyway, that's some of the things we can do with these two identities we just derived. Now, let's see. There's a couple of other interesting identities I want to derive too that are related to this. Let's say I want to save this as a summary sheet with some interesting identities. So I'm going to pull that aside. It turns out that let me remind you that omega plus of E, this Muller operator, was equal to the 1 minus G0 plus of E times potential V inverse. So inverting this operator is of interest. Well, it turns out there's a curious identity, which is this. It's 1 minus G0 plus of E times V, not inverse, multiplied times 1 plus G plus of E times V is equal to 1. In fact, there's an even more general identity where we go into the complex plane. 1 minus G0 of Z times V times 1 plus G of Z times V is equal to 1.
Professor, can you bring the paper down slightly?
Yep.
Thank you.
All right. Now, what this shows you is that the Muller wave operator, which is the inverse of this first factor, is actually equal to the second factor. So let's write it this way: as omega of Z is equal to 1 plus G of Z times V. And therefore omega plus of Z, which we get, excuse me, omega plus of a real energy is equal to 1 plus G plus of a real energy times potential V. Now, how to prove this equation? If I multiply it out, I get 1 minus G0Z times V. It's easier to prove it with complex Z than it is to it's easier to prove it before we take the limits you see under the real axis. In any case, if I multiply this out, I get 1 minus G0Z plus G of Z times V plus G of Z times V minus G0 of Z times V times G of Z times V, multiplying out all the four terms of that product. Now, on the other hand, from these identities we just derived, in fact, the product G0V times G appears in this first version right over here. You can see it's right there, same thing. So this is therefore equal to G of Z minus G0 of Z, still multiplied on the right by V. So the G times V then with a minus sign is going to cancel the G times V with a plus sign. Those go out. And then the minus minus is a plus. We get a G0 of Z times V. That cancels this with a minus sign. And so the result is that it is indeed equal to 1. These two things are indeed inverses of one another. And thus we obtain another identity that I want to summarize over here, which is that omega of Z is equal to 1 plus G plus of Z times potential energy V, or on taking limits, omega plus of E is equal to 1 plus G plus of the energy E times V. Okay. All right. Now, so what this shows us is that if we know the exact Green's operator for the system, then we can find the Muller operator. And finding the Muller operator means we can then map the incident wave into the scattered wave. So this confirms what I was claiming earlier, that the knowledge of the Green's operator, G of Z or its limits, G plus and minus of real energy E, the knowledge of that thing allows us to calculate the scattering solutions. So in other words, we get not only the bound state solutions and the energy eigenvalues for them, but we also get the scattering solutions for arbitrary initial plane wave K coming in from any direction. Okay.
Excuse me.
Yes.
Could you go back to the last page that you just had up? I guess I'm a bit confused, or maybe if you could just explain a little more how you're converting from G of E to G of Z's.
Yeah, so this is the story about Green's operators, is that they're originally defined only for complex values of the energy Z. So for a general Hamiltonian, the definition was given in terms of an integral, but the integral converges if the energy has a complex part, imaginary, non-zero imaginary part, in different ways in the upper and lower half planes. But anyway, it converges, and it turns into 1 over Z minus H when Z is not on the real axis. But we need to have real energies to use to create Green's operators for the real equations we want to solve, in which the energy is real. So what we do is we define G for a real energy, and we have to put a plus and minus sign on it because there's two different ways. Is taking the imaginary part to 0 of 1 over E plus I plus or minus I epsilon minus H. So this is the definition of G plus or minus of E.
Okay.
It's the limit of the Green's operator in the complex plane coming down into the real axis, either from above or from below. And these two limits are not the same. They're certainly not the same on the positive real axis, where you have a continuous spectrum, positive energy continuous spectrum. There's a discontinuity across the real axis.
Okay, gotcha.
Right.
Yeah, I think I just forgot that. Thank you.
In fact, the discontinuity, to remind you, this is from last time, is G plus of E minus G minus of E. We call that the discontinuity. This is minus 2 pi I times the delta function of E minus H, E minus the Hamiltonian. It's a funny operator because it's a delta function of the Hamiltonian. Anyway, that's the discontinuity across the real axis.
Okay, sweet. Thanks.
All right. Okay. All right. Now, so these are some results for the exact Green's operator. Now, next what I'd like to do is tell you about what's called the T operator. used in scattering theory. Let me go back to the formula for the scattering amplitude, which I'll remind you is exact. F of k and k prime is these constants. It's minus 4 pi squared mass m divided by h bar squared times the matrix element of k prime on the left. That's the outgoing wave, potential v in the middle, and then psi sub k as the exact solution on the right. Now, previously I expanded psi sub k in the Born series in order to get the Born series for the scattering amplitude. Now, however, what I'm going to use is this, is that psi sub k is equal to omega plus of energy E multiplied onto the incident wave. And the omega plus of energy E just worked out in the last, in fact, I worked it out and I put it in my summary sheet. So let's pull the summary sheet out. Here's a nice summary sheet. This is omega plus of E is 1 plus G plus times V. So I can put this in. This becomes 1 plus G plus of E times V multiplied onto K. Now, we don't normally know what G plus is. That's, in fact, as I keep saying, that's hard. It's hard to know what the exact Green's operator is because finding it is tantamount to solving everything you want to know about the quantum system. But nevertheless, it makes it an interesting object. If I now use this psi sub k in this formula for the scattering amplitude, then I obtain, as you see, this factor in the square brackets is going to be multiplied on the left by the potential V. And this leads to a definition of an operator called T. It's called a T matrix or T operator. It's parameterized by the energy. And T is given by the potential V plus V times G plus of energy E times V. The second term has the exact Green's operator for the system with the potential energy sandwiched on the two sides. Now, if I make this definition, then the formula for the scattering amplitude is really the same, but it looks more symmetrical now. The same prefactors in front, minus 4 pi squared over h bar squared times the mass m. But now what we've got is a matrix element between plane waves, the outgoing wave on the left, the T operator in the middle, and the incident plane wave on the right. So this is a way of saying that all of the interesting stuff about the scattering amplitude is captured by this T operator. We just need to take its matrix elements between plane waves, incident and scattered waves, and we get the scattering amplitude with this extra constant factor included. So this lends attention to the T operator. Now, the first thing I want to say about the T operator is, well, let's see, I'll tell you where I'm going with the T operator. The T operator is used especially for studying the effects of symmetries on scattering. One would like to know, for example, if the Hamiltonian commutes with parity, then what effect does that have on the scattering amplitude? And that's the question I'm going to address now in the next couple of minutes. Before I go into it, though, let me just mention that there was the AMO seminar. I think it's one of the AMO seminars last Wednesday. I don't know if any of you were there, but it was really quite interesting. It's an experimental seminar. It's given by a guy that's working on an experiment, which he calls, guess what? He calls it Muller. And it involves the scattering of high energy electrons off of electrons, something like 10 or 12 GeV of energy, pretty high energy. And he's doing it. It's part of a collaboration. I think Yuri Kolominsky, I think, is involved in it, I gather. But in any case, it's the purpose of the experiment is to try to measure the electric dipole moment of the electron, which, if it could be measured, would have major impact on the understanding of physics beyond the standard model. In any case, it was all about parity violation, and what effect it has on the scattering cross-section, time reversal, those kinds of issues were all in that talk. So I feel vindicated in giving this lecture now because that shows it is very current. These ideas are part of very current research. In any case, where I'm going with T of E is to show you how it's used in studying the effect of symmetries on the scattering amplitude. In any case, this is the definition of T of E. Now, the T of E, the so-called T operator, it's what people call it the T operator, or sometimes they call it the T matrix. This is really the matrix elements of the T operator. the T operator is not Hermitian, but rather if I take its Hermitian conjugate T of E dagger, what do I get? It's not Hermitian because the Green's operator is not Hermitian. Let's look at that. If I take G plus of energy E, the definition of this is the limit as epsilon goes to 0 of 1 over E plus I epsilon minus the Hamiltonian H. And so now if I take the dagger of that, I get the dagger of this limit. The Hamiltonian is Hermitian, but epsilon, of course, is complex. So under the dagger, that goes into minus epsilon. So the limit as epsilon goes to 0 of 1 over E minus I epsilon minus H, which therefore is G minus of E. It's the Green's operator for these funny incoming solutions, which are not physical. But that's what you get if you take the Hermitian conjugate of G plus. So T dagger of E involves, T of E dagger involves the G of E dagger. This gives us a V plus V times G minus of E times V, you see? So it's not the same operator. All right, now, let's use this nice expression for, here, let me put it in my summary sheet again, because it's a useful summary, is f of k, comma k prime, is the constants minus 4 pi squared mass over h bar squared. And now what I've got is k prime on the left, T of E in the middle, and k on the right. Let's suppose that our Hamiltonian, let's take two cases. Let's take parity and time reversal. Let's suppose a Hamiltonian commutes with parity. And that implies that the Hamiltonian, that implies that the parity commutes with any function of the Hamiltonian, which includes the Green's operators, which are functions of the Hamiltonian. Actually, it commutes with G of Z for any complexified Z, because that's also a function of the Hamiltonian. All right, in any case, in particular, it commutes with G plus or minus. Now let's take this matrix element with K prime on the left, T of E in the middle, and K on the right. And using the fact that parity is unitary, we can write this as pi dagger pi here, T of E, pi dagger pi here, and then a K here. And this one should have been a K prime. That's a unprimed K on the right-hand side. Now in the middle, we've got pi T of E pi dagger, but that's equal to T of E because pi commutes with pi. Since pi commutes with G plus and minus, it's certainly, assuming it commutes with the potential, we'll assume that it commutes with the potential. That's a way of saying it commutes with a Hamiltonian. Then it commutes with T of E. So this pi T of E times pi dagger is just equal to T of E. On the other hand, parity acting on a plane wave of wave vector k changes that wave vector k into minus k. So this becomes equal to minus k prime on the left, T of E in the middle, and minus k on the right. And so what that means then is that if the Hamiltonian commutes with parity, then the scattering amplitude at k prime k is the same as at minus k prime and minus k. I'll draw that with a picture. If we have k, the incident plane wave coming in like this, and then a scattered wave k prime that goes off in that direction, then the scattering amplitude for that is equal to the amplitude obtained by reversing k, coming in from the other side, having a wave coming in from the other side. This is a minus k, and then it scatters in the reverse direction. This is minus k prime. These two amplitudes are the same if parity is good. Good quantum number that commutes to the Hamiltonian. Now, what about time reversal? Let's do that. So first of all, let's assume that time reversal commutes with a Hamiltonian. Assume we have a time reversal invariant Hamiltonian. What does that do to a Green's operator? Let's look at theta 1 over E plus I epsilon minus H theta dagger. This is, and I won't write limit epsilon goes to 0. I'll make that assumed here because I get tired of writing it. But anyway, this becomes in the Green's operator GE G plus of E, you see, is what that becomes in that limit. This is the same thing as theta times G of E plus I epsilon, or G plus of E times theta dagger is equal to this limit. Now, theta, it commutes with H, but it's an antilinear operator, so it converts the plus I epsilon into a minus I epsilon. So this goes over into 1 over E minus I epsilon minus H times theta dagger, which is 1, like this. So time reversal converts G plus into G minus. And that means that time reversal, if I take it around T of E, let's consider this theta dagger. Let's sandwich time reversal around the T operator. The definition of the T operator is V plus V times G plus of energy E times V, like so, theta, like this. And we'll assume that theta commutes with a potential. If it were a real potential V of X or something, it certainly would. We are assuming it commutes with a Hamiltonian. So the V's just goes right through, but the G plus gets converted into a G minus. So this becomes V plus V G minus of E times V. And this is the same thing as T of E dagger, as I just showed you a minute ago. Okay, now let's take this K prime T of E K, which is proportional to the scattering amplitude. And let's assuming that the Hamiltonian commutes with time reversal, let's write this as K prime theta dagger theta T of E theta dagger theta times K. And since theta is antilinear, I need to say which direction it acts. So I'll put parentheses in here to make that clear. Now the middle three factors, theta T of E theta dagger, as I just showed you, is equal to T of E dagger. That's just the line up above. On the other hand, theta acting on K, time reversal acts on a real wave function by complex conjugating. It turns into its complex conjugate. So e to the ikx goes into e to the minus ikx. It does the same thing to the wave function as parity does, as a matter of fact, except theta is antilinear. Oh, I have another step to do here, however. I need to take this theta dagger here and I need to make it act to the left instead of the right. So if we do this, what we get is we get K prime like this, theta dagger. That's acting to the left now. Then we have T of E dagger. And then we've got theta acting on K on the right. And I need to complex conjugate the whole thing because that's the rules that we follow when we change the direction in which theta acts. Now then, this becomes equal to theta, this K prime theta dagger just gives me minus K prime. T of E dagger is in the middle. And theta K just gives me minus K. But this is complex conjugated. So that's the same thing as reading the matrix element backwards. It becomes minus K T of E times minus K prime. Okay. So the result of this is that the F of K comma K prime, if the Hamiltonian commutes with time reversal, is equal to F of minus K prime and minus K. Like so. Or if I draw a picture, it means that this same picture here, K and K prime, is the same thing as if the minus of the incident wave, so we have minus K prime is now the incident wave coming in, you see, and the scattered wave is minus K going out like this. Okay, and this is the result of the effects of parity and time reversal conservation on the scattering amplitude. Interestingly enough, if you combine both parity and time reversal together, PT in other words, what you find is that F of K comma K prime is equal to F of K prime comma K. This is sometimes called detailed balance, that in terms of in statistical theories, it's called detailed balance. It means that the rate at which the reaction goes in one direction is the same in which it goes in the other direction. If you think about states populated by different K values, In any case, this is detailed balance. It requires PT pi theta, or PT would normally be called PT symmetry. Okay. Okay, so that's the story in the T matrix. Any questions about that? All right, then. The last topic having to do with formal scattering theory is going to be the orthonormality relations. So we have these scattering solutions, psi sub k, and a number of exact relations involving them. Also, I hope that you understand you have a visual idea of what those wave functions look like. You know, they look like an incident plane wave coming in, hitting our scatterer like that, producing radiated outgoing waves in all directions like this with some angular dependence. That's the picture we have. And there's a fixed wave field filling up all of space here with a given frequency. It's an energy eigenfunction, so it's a stationary state. It's associated with a wave vector k of the incident wave. This is what in Ket language I'm calling psi sub k. It's an exact scattering solution. So it's an energy eigenfunction. Now, for discrete energy eigenfunctions, we know that they're orthonormal one to another. Are these orthonormal? That's the question. Now that we're in the continuum now. Are they? And if they're normalized, is that in a continuum normalization? That's the question we want to answer. So what I'd like to do now is to take a look at the scalar product psi k prime, scalar product with psi k, like this. So get this, these are two different scattering solutions with two different k vectors. So there's you have one k vector coming in like this, and you might have another one coming in a different direction, k prime. And in fact, will allow the energies to be distinct as well. So they not only made the directions be different, but the magnitudes of the k's might be different as well. Let's keep that in mind. Anyway, in any case, we would like to compute this scalar product in general and see what we get. So the first thing to do is to get one of these. Let me get my summary sheet here if I can still find it. Where is it? I guess this is it here. It isn't actually on the summary sheet. Let me just go ahead and write it down here. So what I want is this: is I want the there's two versions of the Lippmann-Schwinger equation. There's this one, which is that the original one we started with, that psi k is equal to k plus G0 plus of energy E times V times psi k. That's the original Lippmann-Schwinger equation. Now, however, we also found that the molar wave operator, omega plus of energy E, is equal to 1 plus G0, 1 plus G plus of energy E times V. And this means that the psi sub k is equal to this thing, 1 plus G plus of E times energy V acting on K. That's the same thing as K plus G plus of E times V acting on K. Now let me take this equation and rearrange it by solving for this K here. I'll write it up here. We get K is equal to, there's this K. On the other hand, on the right hand side, we're going to get the psi sub K. And then what I'm going to do is bring this term over to the other side. So it comes in with a minus sign, G plus of E times V times K. And let me box these two equations to draw attention to them. So as I just explained, the first equation is the usual Lippmann-Schwinger equation. The second equation can also be thought of as a Lippmann-Schwinger equation, but in kind of a funny reverse kind of a way. So let's imagine a world, some kind of weird world where we could solve the exact problem with the potential, no trouble at all, but we don't know how to solve the free particle equation. So that means that the equation we'd like to solve would be this, is that E minus H0 acting on K equals 0, where K is we can pretend that we don't know what it is. That's the unknown. How am I going to solve this? Well, I can do it like this. Let's write E minus H0 and subtract the potential V on K, and then compensate by putting minus V on K on the right-hand side. And the left-hand side is, of course, E minus H acting on K. So now you can see that if we regard the right-hand side as a source term, then if we have the exact Green's function for E minus H for the full Hamiltonian, we can use it to solve for K. And if we do, what we get is that K, the solution, is equal to that. First of all, there's a solution of the homogeneous equation. That's a solution of the exact system, E minus H. Let's call that psi. And then we have to add to that the Green's operator for the full Hamiltonian H acting on the right-hand side, which is minus VK. So we have a minus sign there. We then have a G plus, not a G0 plus, but a G plus for the full Green's operator, V acting on K like this. So this becomes a Lippmann-Schwinger equation in this kind of inverted world where we know how to solve the exact problem but not the unperturbed one. But in fact, it's exactly this equation I derived up above. So this equation I derived above shows you that, in fact, if you do this, the psi that comes out here is actually the psi sub K. It is the homogeneous solution you want to put in here is the exact solution of the scattering problem. All right. Now, with these two identities, then these two versions of the Lippmann-Schwinger equation, let's look at this scalar product. So first of all, I'm going to take the second equation and solve for psi sub K. Psi sub K, bringing this across, is equal to K plus G plus of energy E times V times K, like so. And then if I take this matrix element and bring this down, this is the matrix element that we want. And I substitute this psi K on the right-hand side here. And what I get is this becomes equal to psi K prime as a bra multiplied onto K vector, it's this thing, plus psi K prime as a bra multiplied onto G plus of energy E times V times K. All right. Now let's work on this second matrix element here. Let's write out explicitly the G plus of E. This becomes psi K prime as a bra, and then I have 1 over E plus I epsilon minus H, and I'll have the limit epsilon goes to 0 being understood here. Then we have V, then we have K, like that. Now I've got the full Hamiltonian H adjacent to an eigenstate of itself, which is psi sub K prime. The energy of this state is, let's call it E prime, which is equal to H bar squared K prime squared over 2M, prime version of the energy. So this H can be replaced by E prime when it acts to the left on its own eigenstate. And therefore this thing in this fraction that we see here becomes just a C number and can be taken out. So the whole thing then becomes 1 over E plus I epsilon minus E prime. It's E prime there, times the matrix element psi K prime, V, and K on the right. Okay, that's what's left of this. All right. Now then, that takes care of the second term. Now let's go back to the first term. Let's take the original Lippmann-Schwinger equation, which I've gotten up here, and let me write it again, except I'll replace K by K prime. So we have psi sub K prime is equal to K prime plus G0 plus of energy E prime times potential V times psi sub K prime. And now let me take this and convert it into a bra. Permission conjugate everything. Psi K prime bra is equal to K prime bra. And then taking this into a bra, I read it backwards. It becomes plus psi K prime as a bra. We have V as Hermitian. But G is not Hermitian. I take the Hermitian conjugate of G0 plus, it goes into G0 minus, because the E plus I epsilon went into an E minus I epsilon when I complex conjugate it. So now I want to take this psi k prime and plug into there. And when I do, what does this term become? It becomes scalar product of k prime with k. And then we have this term here. It's going to be plus psi k v G0 minus of energy E prime applied to k. That's the state there. All right. Now we've got G0, this G0 minus of E prime is the same thing as 1 over E prime minus I epsilon minus H naught. That's what it is, with the limit epsilon goes to 0 understood. But H naught is adjacent to an eigenstate of itself, of wave vector k, so H naught can be replaced by E, which is understood to mean H bar squared k squared over 2m. It's the energy associated with this plane wave. And so what we get then is a C number that can be taken out. And so this entire second term then becomes the following. It becomes 1 over E prime minus I epsilon minus E times the scalar product psi k v k, like so. And now if you look at this term that we computed and this one up here that we computed, you find that they're equal and opposite to each other. The matrix element is, this should have been a k prime over here. See, where am I? Yeah, this should have been a k prime. K prime here, k prime here. That makes these matrix elements equal, but the prefactor is equal and opposite. This is E plus I epsilon minus E prime. This is E prime minus I epsilon minus E. So these two terms cancel each other out. All that's left is a k prime scalar product. And the grand conclusion is this, is that psi k prime scalar product with psi k is equal to the scalar product of k prime with k. That's to say it's the same as the scalar product of the incident waves, which is the direct delta function of k minus k prime. So these scattering solutions then satisfy the obvious continuum normalization orthonormality condition that written here in terms of the k variables. I think this derivation is tricky. I always have to review it before I can derive it again in a lecture. But on the other hand, I don't think it's possible. I wouldn't have any idea of how one could ever derive this from the Schrodinger equation. You need to use these Green's operators to get this, and it's the only way I know of to do it. But it's an interesting result because it means that these scattering solutions, which are the obvious steady states that result when you send plane waves at targets, they end up having a simple orthonormality relationship, not only normalization, but also orthonormality amongst themselves. Now, by the way, I carried this out for the outgoing solutions, what we called psi plus. To make that explicit, I can put a plus in here like so. It turns out that there's the same orthonormality conditions for the incoming solutions. Psi k prime with a minus, psi k prime with psi k with a minus, also have the delta function orthonormality conditions. But the incoming solutions are not linearly independent of the outgoing solutions, rather they're linear combinations of each other. So in effect, what we have is two orthonormal sets here that span the same space. The space they span is the set of all scattering solutions, positive energy solutions. It's not the entire Hilbert space because there may be bound states. And this shows up when we do a resolution of the identity. The resolution of the identity is the following. It's this 1 is equal to the sum over the bound states. If I use the notation I've been using earlier, it's the outer product of n alpha, n alpha. There's the bound states. But then we have an integral, b cubed k, of psi k outer product with itself. Here is our scattering states. So this is the orthonormality condition for the problem, including both bound states and scattering states. Okay, that's all I want to say. Oh, maybe one more thing. one more thing. This leaves open an interesting question, which is if the outgoing states form an orthonormal set, which if you include the bound states becomes complete, and the incoming states form an orthonormal set, which if you include the bound states becomes complete. By the way, I just need to, I can just make this plus or minus here for both of these to indicate that this can be either incoming or outgoing for spanning the scattering states. This raises the question about what is the scalar product of an incoming state with an outgoing state? What is this scalar product equal to? And it turns out that this is the S matrix, which is a central object in scattering theory, and it's used for all sophisticated treatments of scattering is the S matrix. And I may lecture on the S matrix later in the semester, but not now. It's too much for now. The S matrix is necessary for relativistic quantum mechanics because it can be made relativistically covariant, but that's not its only application. It's actually used everywhere in scattering theory. Okay, this is all I want to say for now about scattering theory. Are there any questions about this? This is what's called formal scattering theory. I think you'll understand this better after doing the homework problem next week. It's going to be a one-dimensional version of this. This is where you can actually work out not only the unperturbed Green's function, but you can work out the exact one too for some potentials, delta function potential anyway. And so you can go through the calculations explicitly and see how all these relations fit together.
So I had a question. Under time reversal symmetry, do you have some relationship between the incoming and outgoing?
Yeah, let's see, I drew the picture back here. So if you have time reversal invariance, it means the scattering amplitude is the same. You can see why it's time reversal, because what you do is you say the scattering amplitude for an incident state K and an outgoing state K prime is the same as if the outgoing state was reversed, time, coming back in other words, and the original incoming state was also reversed, so that's now an outgoing state. So it's a complete reversal, you see, of the incoming and outgoing states with a change in sign of the momentum. So that's what time reversal invariance does to the scattering amplitude, and indeed it's actually kind of obvious what it does. Whereas parity just flips the K direction, and again that's kind of obvious too.
To the amplitudes, is it obvious that the incoming and outgoing states are the same?
Well, the scattering amplitude. Oh yes, I see what you're saying. Yes.
It might be true.
That's a good question, and I haven't actually thought about that. So this is the exact scattering amplitude. So this certainly affects the cross section, which is what you observe. So this is direct impact on what one observes, depending on symmetries. And by the way, if the symmetry is broken, then you need to go through this analysis to see what to look for, in the scattering experiments. That's just what these guys are doing. These people are doing on this molar collaboration. In any case, you're asking about the scattering wave function.
Yes.
Well, the wave function is not a function of two Ks. Scattering solution is a function only of the incident K.
Sort of seems intuitively clear from the name that the incoming should be the same as the outgoing, but I don't know if that's actually true. If it's
well, the scattering solution doesn't really have an outgoing K. It has an incoming K, and that's all. I mean, the outgoing wave is a spherical wave at large distances. It is anyway. So, I think there's an intelligent answer to this question, but I don't think I can put it together in my head tonight. But one of the things one would have to do is to understand exactly what you mean by by the effect on the scattering solution. Any other questions?
I have a question on the jargon. Why do we keep calling these things wave fields instead of just waves?
Well, you can blame me for that. I don't, because it is a field. it's a field, and these are, what the problem we're doing here is scattering in three-dimensional space, so it's a wave function in 3D. If you prefer to call it just a wave function, that's fine.
Okay, I see. Thank you.
Was there another question?
I actually had another just logistical question.
Sure.
Someone else in my department was interested in listening in on the like electromagnetic field Hamiltonian stuff. Are we doing that next week, or are we doing notes 39?
I'm going to do adiabatic invariance before
Okay.
doing the electromagnetic field, so it might be another lecture or so before we get it. We'll probably get to it next Thursday, though.
Okay.
Yep. Okay. Okay. So I got 10 minutes left to start to tell you about adiabatic invariance. So in mechanics, as in contrast to statistical mechanics, the word adiabatic usually means a process which is dependent on, which is time dependent, but is in which the time dependence is only slow. Whereas it has a different meaning in thermodynamics. In any case, to give you an example from classical mechanics, let's take the case of the pendulum with a slowly varying length. Let's suppose we've got an upper floor like this with a hole in it, like so, and there's a rope that goes down like this, and it connects to make a pendulum coming down. There's a pendulum bob like that, and it swings back and forth with some amplitude like this and oscillates back and forth with some frequency. The pendulum has a length L, but there's a guy or a lady or somebody in the upper room who can pull on the rope and thereby change the length of the pendulum, so L becomes a function of time. Now, the standard formula for the frequency of a pendulum is the square root of L over g, the acceleration of gravity. So if L is a function of time, then omega is also a function of time. Frequency becomes a function of time. The person that's pulling on the rope or letting the rope out gets to control, how omega depends on time. That's under, in effect, under experimental control, we might say. Okay. Now, what makes the system adiabatic is if the change in frequency during a single period is small compared to the frequency. So if I call delta t the period of oscillation, that's 2 pi divided by omega. And so delta omega then would be equal to omega dot times delta t, which is equal then to omega dot over omega times 2 pi. And we want to require, if it's adiabatic, we want this to be much less than omega. The change in omega over a single period is much less than the frequency itself. If we ignore the 2 pi because we're just doing order of magnitude, then this is equivalent to saying that omega dot divided by omega squared is much less than 1. And this is the condition which we would impose on this pendulum problem in order to be under adiabatic circumstances. If this condition is not true, if it's not adiabatic, then we have to say, well, it's not a slow time evolution, and then adiabatic theory does not apply. And instead, what we have is just some general time-dependent Hamiltonian system that we have to solve however we can. But in the case that the motion is slow, adiabatic in this sense, there are special results, and that's what I'm going to be telling you about. Okay, now the motion of a pendulum, small amplitude motion of a pendulum is, to good approximation, is a harmonic oscillator. So one of the ways of modeling this problem is to write down a mechanical harmonic oscillator, p squared over 2m for the kinetic energy, plus m omega squared over 2 times x squared for the potential energy, except the omega is a function of time. So it becomes a time-dependent Hamiltonian, both in classical mechanics and in quantum mechanics. It's a time-dependent Hamiltonian. Let's just talk about the classical mechanics for now. It's a time-dependent Hamiltonian. So we want to think about the frequency varying slowly. So if we look at the frequency at one time, then it just has some value and it doesn't change very fast. So that gives us an effect which you might call a frozen Hamiltonian at that particular period in time, which is just an ordinary harmonic oscillator. That harmonic oscillator there's a certain energy if it's evolving in time. There's a certain energy it's swinging here with a certain energy. So that means that there's an orbit in phase space, x and p here, which is an ellipse because the Hamiltonian contours the Hamiltonian give us an ellipse. So if this is at t equals 0, this is the equation H0 is equal to E0, where E0 is the energy at t equals 0, and H0 is the Hamiltonian evaluated when omega is evaluated at t equals 0. Now, if we wait long enough for the frequency to change substantially to a new value, it might be only half as much as it started out with, for example, but we do it slowly, so it took many oscillations to get there. The Hamiltonian still has this form. It's still a quadratic function of Q and P, and its contour lines in phase space are still ellipses. But the parameters of the ellipse have changed. So maybe it's moved into a new ellipse that might look something like that. Let's just draw this here. Okay, so let's call this H1 is equal to E1. H1 is the new Hamiltonian, which omega has a new value that is taken on after the slow time evolution. And what is E1? Well, E1 is the new energy. E1 is the new energy. E1 is not the same as the old energy. This energy is not conserved in this process. How do I know energy is not conserved? I know because the person that's pulling the string up on the upper floor has to do work to pull the string up, or release work and letting it down. So energy is not conserved. And therefore, the energy value, E1, here, is the question arises, is what is the value of E1 that we should put in there to draw the orbit for the classical system at the final time? So what we're imagining here is that the E0 is that the transition from H0 to H1 is determined by the person controlling the string. Therefore, we know what the initial and final frequencies are. We know what the initial and final Hamiltonians are. We also know, let's suppose we know anyway, the initial energy. We knew what the initial energy was when the thing started. The question then arises, what is the final energy and how would we know it? Well, the answer to that question is given by the following rule, which is obviously the shape and the size of the final ellipse is going to depend on the value of E1. And here's the rule. The rule is that the area of the original ellipse is equal to the area of the final ellipse. That's the content of what's called the adiabatic theorem in classical mechanics. Now, the area of the ellipse can also be written as the loop integral of p dx taken around the orbit. If we divide by 2 pi, we get what's called the classical action I of the orbit. We saw this last semester in WKB theory. And what the classical adiabatic theorem says is that the system evolves in such a way that the area, that is to say the action, is conserved. Now, it's not conserved exactly. It's only an approximate. Adiabatic invariance is only an approximate conservation law. But the conservation works like this. Is that if I made the transition from H0 to H1, let's say in 1 minute over some period of time, then I'll find there's a certain error in the action. The final area is not exactly equal to the initial area. But then if I make the same changes between H0 and H1, but I do them more slowly, like 10 times more slowly, so I do it in 10 minutes instead of 1 minute, then the error in let's say the change in the action delta I between the initial and final values becomes smaller. In fact, it approaches 0 the more and more slowly the change is carried out. So the conservation of action is never perfect over any finite rate of change from H0 to H1, or that is to say, from some initial frequency to some final frequency. But the slower we do it, the more accurately the action is conserved. Now you can get into more refined theories to find out how does the error, the delta I, depend on the slowness parameter. And under some certain circumstances, it turns out it has an exponentially powerful dependence on that, so that goes like e to the -1 over epsilon is the idea. In any case, that gets off into classical adiabatic theory, which I don't want to go into. But in any case, this is a brief summary of some features of classical adiabatic theory. And what I'm going to do in next lecture is to launch into the corresponding quantum theory. So I'm out of time. So that's the place to stop. Are there any questions about this, just this classical part?
I have one question. So, are the change of actions only depends on the speed of the change, or also depends on the E1 minus E0, the absolute energy change?
Well, the action is a function of the energy. So if I know how the action changes, then I know how the energy changes. In fact, that's what determines how the energy changes. E1 is determined by the fact that the final area is equal to the initial area. The area
Okay.
is the action, you see.
Yeah, thank you.
So we knew what the final Hamiltonian was because our experimenter, determined the length of the pendulum and therefore the final frequency. So the H1, the functional form of it, is known. But what we didn't know was which contour line are we supposed to draw, i.e., in other words, what is the energy of the final system? And that energy is not conserved. The way to find out what the final energy is to equate the areas together. You know the initial area, you know the initial energy. Well, you know the initial Hamiltonian, you know the initial energy. That determines the curve, initial curve, and therefore the area. And then what you do then is you use that to determine the energy of the final curve. So that's how you solve adiabatic problems in classical mechanics. Any other questions? All right. If not, then that's all for tonight. And let me stop screen share. All right.